Good. So today I have basically one main goal. My goal is to talk you guys through the development of scientists' knowledge of what matter is. Earlier in our unit, we talked about the word matter. Can anyone give me a definition of matter again? Go for it.
Anything that has mass.
Yeah, it has to have mass, which means it has to weigh something, it has to take up space. My goal today is to walk you guys through how scientists have been slowly but surely studying matter, because really that's what chemists do. Chemists study the change in matter. And so today's lesson is actually more of a history lesson than anything else. We're going to go through about 3,000 years worth of history, and then when we finish at the end, we're going to come to our current understanding of what matter is. Does that make sense? So most of it, again, I'm not going to read off of my slides. I hate doing that. I'm not a teacher who's literally going to say, an early branch of chemistry was metallurgy. So what I'm going to do is I'm going to talk to you guys as a story. Please write down the stuff I say. Does that make sense? So I want you guys to imagine 3,000 years before Christ, which basically puts us 5,000 years ago. We're talking almost like the Stone Age. Okay. If I use the phrase the Stone Age, do you guys think of say the Flintstones? Everybody watch the Flintstones? Right? Yeah. So we're talking about a time in civilization where the tools that people had were pretty crude. I mean, ignore the Flintstones, that's big, obviously, right? But we're talking literally if you wanted to, let's say you were a hunter and you wanted to kill an animal. You probably you were throwing a rock at it, or you threw a stick at it, or maybe you were really smart and you put a rock on a stick and you tried to stab it, right? That's the time frame we're talking about. Can you kind of picture in general what this would have been like? Well, imagine the first person, and I mean, I don't have a name of someone who figured this out, but imagine the first, and we'll call him a scientist, who figured out how to produce a metal. Right? So that rather than working with stone, now they're working with iron or carbon or copper or something else. And they found these rocks in the ground, but they're not like rock rocks, they're ores. You guys ever heard that word ore before? Like you find in a mine, right? And they figured out a way to refine these metals to make themselves pure copper or pure iron. And all of a sudden, rather than making your spear with a rock, well, now you're able to put some metal on the end of it and sharpen it. And all of a sudden now you can make a spear or a bow and arrow or something else like that. You got what I'm referring to here? The name we give to this age is metallurgy, where really they're starting to work with metals. Now, most of the metals I have listed here, some of them were used as, say, weapons, or maybe as gardening tools. If you were a farmer and you all of a sudden were able to make some sort of plow, the plow, if it was made out of a rock, isn't nearly as good as if you can make a plow out of, say, a piece of metal, a piece of iron. You get what I'm saying here? Another place you would have used things is actually jewelry. We have evidence in ancient times that, we still do to this day, gold and silver were very, very valuable. But the reason why gold and silver are valuable is the opposite of copper. They're valuable because they're soft. And because they're soft, we can mold them into jewelry, into shapes, into rings, they didn't use watches back then, but take anything that would be considered pretty jewelry, right? That's what gold and silver were used for. Whereas copper and iron, we like those ones because once we melt it and form it and shape it, what happens when I melted that tin the other day and it reformed? Was it still in a soft shape or did it re-harden? Right? And so what they can do is they can mold it into a shape, make a tool out of it, and now it's and now they've made a hammer or a nail. Does that make sense? So this is the era we're kind of talking about where people wouldn't necessarily consider this to be science, but yet really this was primitive science. The word I need you guys to know is this one down here. So maybe you want to highlight this. It's called an alloy. If you haven't heard this word, an alloy is where you melt and mix metals together. And this really advented into human history a new age where rather than it being the Stone Age where you're working with rocks and sticks, well, now we're using metals. And you can do so much more with that. Does that make sense? Do I have it on the slide here? I don't have it on the slide here. You guys ever heard of the phrase called the Bronze Age? Maybe you've heard that phrase before, the idea of when bronze was discovered. Because this really was big. the idea of melting copper and tin together. One of the downsides, though, to the Bronze Age is that it actually caused more weapons. And now fighting always, war, always seems to take leaps and bounds whenever a new scientific discovery is made. Right, let me go through the idea here. Let's say that people are fighting and they're literally using rocks and sticks. But then someone discovers how to make bronze and they make a sword out of it. Who wins, rock or sword?
Make a raw steel.
Okay, you guys get my point though, right? But then fast forward in human history, and all of a sudden someone discovers how to make gunpowder, and now there is a gun in play. Who wins between gun and sword? Well, now gun wins, right? Probably the most recent example of this happened in the 1940s. Anybody know what happened really big in the 1940s? The atomic bomb is the big one. Yeah, and it's still a problem to this day, especially with North Korea. If you guys don't follow the news a lot, North Korea is trying to work on making atomic bombs. And that becomes a bigger issue because as new technology and new science develops, unfortunately it becomes more and more easy to kill people. And that's usually not a good thing. But that was one of the advents of, say, combining copper and tin is now you can make a sword. Right? And then literally kingdoms and empires were forged. Guys, please focus. Okay. I'm going to start calling you guys out here. I need better. Empires were forged based on like whoever had the technology was able to then go out and win better fights. Does that make sense? So on my next slide, I kind of go on to this as well. Eventually, a compound was made called steel. Steel was formed from iron and carbon together. And I mean, steel was really big. I'm thinking during medieval times. Because now we're talking about knives, armor, and swords made out of steel, which is even better than bronze. Right? And so now if you can make yourself chainmail and armor and a really, really good steel sword, well, the guy over there with a bronze pole is totally going to lose in that fight. You know what I'm talking about here? So this is really where our history starts. We're talking through history. Most science has actually originally been used to like make some sort of technological advance. But the truth is, at this time, they didn't really know what the stuff was made of. Okay? Well, I'm going to call them scientists because they were trying to discover new things. But I don't think they really knew what they were using yet. And here's the big reason why. Microscopes hadn't been invented yet. Microscopes weren't invented until about 200 years ago, give or take. And so if we're talking medieval times and Bronze Age and Stone Age, we didn't really know what stuff was made of. And so at the time, really all the scientists were doing is they were doing something called philosophy. They had ideas, but they really couldn't prove them. And maybe you've heard of this guy before. One guy you used to know about, his name is Aristotle. Have you ever heard of Aristotle? He's a philosopher. He had this theory. He thought that everything that was matter was made up of either air, fire, earth, or water. He was not even close. Not even close. Okay. Although water is kind of something that we use a lot of, like fire, for example. Fire is not even matter. Right? Fire is energy, not matter. And so even though air is matter and water is matter, and I guess earth is like a mixture of matter, really, he was not even close. He had another guy around his same time. I want you to know his name. His name was Democritus. And he actually had a really good idea that we still use a little bit to this day. He had a thought, and I'm going to illustrate it using a sheet of paper here. Democritus suggested that this is matter. And he thought that if I cut it in half, and I cut it in half again, and I cut it in half again, and I just keep cutting it in half, he figured that eventually there's got to be a point where I can't cut it in half anymore. He feels like there's got to be a limit somewhere there, where like it's not possible to go any smaller. Does that make sense? That was Democritus' idea. It's actually quite smart. And so he coined this term, a Greek word. He used the word atomos. And we still use this word to this day because we use the word atom. Yeah. And literally the word atom in the original Greek comes from the word indivisible. Democritus had this idea that maybe at some point, if I keep making it smaller and smaller and smaller and smaller, there's got to be a point where I cannot cut something in half. And that's as small as it gets. And what's amazing about Democritus on this one here is that he didn't have a microscope. Right? Like this is thousands and thousands of years ago, but he was actually right. We still use that word to this day. Now, I want to fast forward a little bit in our timeline here to a group of people called the alchemists. And maybe you've heard of them before. Alchemists are kind of like magicians and sorcerers mixed with chemistry. They had one goal. Their goal is to become very rich, like everybody at the time, right? And you maybe heard this before. He who has the gold makes the rule. If you had gold, you were rich. And at this point here, scientists were starting to learn about some of the elements in the periodic table. And they knew about one called gold, which is very valuable. And there was one very, very similar to gold. It was almost exactly as heavy. It had some similar properties, but it wasn't valuable. It was lead. And so these alchemists, they had a goal. They wanted to try to magically turn lead into gold. That was their goal. They were kind of magician sorcerers. I have that right here. They want to turn lead into gold. Unfortunately, it never worked, which actually probably makes sense right now, because literally if this did work, if you could turn lead into gold, then everybody in the world would have gold, and we'd all be rich. So we'll talk about the reasons why this was impossible a little bit later, but that was their goal. One of the cool things about the alchemists, though, is that although they weren't successful in their goal of becoming very rich, there are two developments in science that are probably worth noticing. The first one is that they were the first scientists to start working with things like hydrochloric acid. They started working with a lot of new compounds and chemicals. They were very creative, I think is the word. They like to explore and combine and let's see what happens. Right? Now, nowadays, I think that's actually quite dangerous. I'm not going to give you two chemicals and say, here, just pour them together, because what if they make a toxic gas? Okay? But, these guys were some of the original scientists who were like, hey, let's see if we can turn this into gold. You guys ever heard that story of like King Midas, like the legend of King Midas, where everything turns into gold, right? We're talking that time frame here where people wanted to become rich. Here's the other really cool thing, though. They also were very meticulous in their work. And if you know what meticulous means here, like they had high standards. Okay? Previous to this, scientists and chemists, if you could even call them chemists, because maybe they weren't quite to that point, but people who were trying to do science, if they wanted to store their chemicals, they stored them in clay pots. Okay? Because literally that's what things would get stored in. They would put your water in a camel skin, or you'd have a pot, but it was made out of clay. Well, when you store your chemicals in a pot out of clay, it slowly but surely contaminates them. They were brilliant here. They were the first people to realize we should store our stuff in glass. We still do that to this day, right? All of the beakers that I have on the side here are made out of glass. And it's really easy to clean them. They don't stay dirty, and most importantly, they don't contaminate the other chemicals. Can you imagine putting our chemicals into a piece of pottery? It might work for like a day or two, but even over time, I'm not even sure I'd drink that water because maybe lead would leach into the water. So, although the alchemists didn't actually succeed in this whole lead to gold idea, I wanted to include them because they made some noteworthy accomplishments. Okay. So here's the first scientist I want you to know his name of. Okay. This guy is Antoine Lavoisier. If you want to know how to pronounce it, it's pronounced Lavoisier. He was French. Okay, Lavoisier. And he came across one of the most important discoveries while doing experiments. And you probably have heard this bolded word down here before, or this bolded phrase. He discovered something called the law of conservation of mass. And if you haven't heard that before, let me try to describe that to you with, I think, my next slide here. No, I don't have a picture of it. It's in one of my other sets of notes. Here's what Lavoisier did. Lavoisier burnt some stuff. Okay. He took, let's say, compound X, and he combined it with compound Y. And when he was done, it turned into something new through a chemical reaction. And what he did is he weighed it. And when he weighed this, it was like, say, 10 grams. And when he weighed this, it was 30 grams. When he was done, after he combined the two things he started with and weighed them, he discovered that this plus this always equaled the final amount. And he discovered that mass always seems to be conserved. So if you start with 5 grams, you should always end with 5 grams. If you start with 20 grams, you should end with 20 grams. And this actually makes a lot of sense as well. One of the reasons why it makes sense is that if mass could be lost, if I could lose mass, then slowly but surely our universe would be decreasing in mass. And eventually we would just decay away to nothing. So it's actually really good that mass is conserved. Whatever we start with, we always finish with. And this was really important. We're actually going to spend a whole lesson on this a little bit later in our course. But that was one of Lavoisier's concepts, is that he realized that mass was conserved. He also had one more important contribution. At this point in history, we're talking about 1780, give or take. Okay, so this is, in the grand scheme of things, it's actually fairly recent. Okay, because I mean, we started our lesson talking like 5,000 years ago. His idea here was we should have a common naming scheme. Okay. He realized that if I'm going to talk about this as this item, and if I'm going to talk about this as this item, we should all use the same words. Okay. The English language is a good example of this, where I might say that that is a hat, but I might also say that it's a cap. Which one is it, a hat or a cap? In chemistry, that's bad, because I can't call this a something and then have somebody else call it something else. That gets confusing. We should have one word for it. Does that make sense? And so Lavoisier is kind of the one that we credit with saying, look, you can't call this A, and you can't call the same thing B. We all got to be on the same page here. Does that make sense? And so he came up with a universal naming system. And we're going to learn about this in a couple of days as well, on how to name chemicals. But we still use that to this day. And because of this, some people actually called Lavoisier, they gave him the name the father of modern chemistry, because really, if it wasn't for him kind of consolidating the whole system, we literally might have like 10 different names for every chemical, and it would be impossible to know what we're talking about. So he actually made that really important contribution. Okay, next person. If I could give some advice, guys, just because I know what's on your future tests and assessments, it would be really worthwhile for you to highlight and study this slide. Because this guy right here made some contributions that I'm going to test you on for sure. These 4 points down here. So we're talking again about the 1800s time, and a scientist named John Dalton wanted to revisit the idea of what is matter made out of? What is our stuff made out of? And he put forth a paper. He kind of wrote something to the scientific community and said, here are 4 things that I think are true. Now, he didn't have a microscope. So he didn't have the ability to test this and like zoom in and look. But here's his 4-point theory on what mass was made out of. Here's the 4 points. The first one, he thought that all matter was made of small indivisible particles called atoms. That was his first point. Basically, he stole Democritus' idea and said, look, at some point, you can't get any smaller. He decided to call it an atom. Second point, he said that all atoms of an element, he thought that they were all identical. Here's what this means, by the way. What he was meaning is that if this is iron right here, and if this is iron over here, then this iron and this iron have the same properties. So this iron, if it weighs 5, that iron over there better weigh 5. If this iron over here has a +3 charge, this iron better have a +3 charge. That was his theory, is that all atoms of an element must be exactly identical. He's actually not right about this. We're going to explain why a little bit more later, but Dalton was not perfectly correct, because it's actually possible to have different masses and charges for different elements. Third thing, he believed that different elements have different properties. So not only does this iron here have to match this iron over here, but this iron here better be different. This iron here better be different than this carbon. You guys get what I'm saying here? One point is that iron better match iron, but the second point is that iron better not match carbon. If we're going to call it something else, it better be entirely different. So iron better be different than carbon, and carbon better be different than oxygen. They all must be different. He's right on that one. The last one is kind of hard for kids to interpret, so I need to kind of write it out for you here. He also suggested that different elements are able to combine in a specific fixed ratios. Here's what he meant. He meant that we could take, like, say, 1 carbon and add it to 2 oxygens and make a new compound. Do you guys know what that's called? Yeah, carbon dioxide. And what he was meaning is that there was a fixed ratio. There's 1 carbon for every 2 oxygen. That's what the fixed ratio means. It refers to like those little numbers down there. He was right about this. Well, for example, here's another one. If you take 2 hydrogens and attach it to 1 oxygen, this is now a fixed ratio compound. Make sense? The ratio is 2 hydrogens to 1 oxygen. So for the most part, Dalton's theory was actually pretty close to being right. but a few of his items needed to be tweaked over time. This right here wasn't quite right. And this one right here wasn't quite right either. And what I want to do over the next few slides is talk about some scientists who kind of furthered the understanding of what matter is made of. Anyways, if I give you some advice though, Dalton's 4 points is something you should know for the test that we're going to write eventually. Okay, so if you want something to study, put a big star and make sure you remember those 4. Wait, the next scientist I want to talk about is a guy named Dmitry Mendeleev, who I believe was Russian, or part of that Russia-Ukraine kind of area. Dmitry Mendeleev is credited with making the first known periodic table. Here's what he did. He started to recognize that of all these elements that we started to know about, carbon, and copper, and oxygen, and nitrogen, he started to realize that many of them have similar properties. And so what he did is he wrote all of the information he knew about them onto a card. So like, for example, he wrote down hydrogen. It's a gas. It's very light. It reacts in this way here. And then he wrote down helium. It's also a gas. It doesn't react with things. And he wrote down all the properties that he could. Then what he started to do is he started to put all of them together in groups. And so things that were similar to each other, he grouped them together. And eventually he started to make kind of a chart out of it, where he started to have up and down things. We now call those groups. And he also started to go across with things like that are rows. And he started to kind of put a chart together. And he kind of made the first ever periodic table. Now here's one of the most amazing things about this to me. As Mendeleev was putting together his periodic table, of all of these substances known to people at the time, he actually left some gaps. This is really cool to me. This is a picture of more or less one of Mendeleev's first periodic tables. He actually left some holes in his table. And he said that one day, I predict that we're going to discover an element that we currently don't know about. And the most amazing thing is that in the future, someone did. There's actually 4 elements where when Mendeleev made his table, he left a hole there and said, right here, I believe one day we're going to find an element that will go here because it's going to have similar properties to everything that's kind of around it. But we don't know it yet. And the cool thing is one day scandium was found and it totally went right there. Which, I mean, to me that's amazing, that he can make that prediction and be right about it. We're going to talk about the periodic table a lot more tomorrow. That's my goal for tomorrow, is to talk about how the periodic table works. Wait, next scientist I want you to know a bit about. His name is J.J. Thomson. He was doing an experiment with something called a cathode ray tube. Did I write that on here? I did not. Here, let's write that down on here. He was working with something called a cathode ray tube. Wait, brief aside. Does anybody maybe still, their parents still have like one of those like old box kind of TVs? You know the ones I'm talking about? Not the flat screens, but like the old school ones that are like cute.
Yep.
Okay. Inside those TVs is a cathode ray tube. Okay. Literally what it is it's an electron gun. Okay. It shoots electrons. And the way it works on your old school TV is it literally shoots in rapid fire. It shoots a whole bunch of electrons at a screen. And then as those electrons hit the screen, it either lights the screen up in red, green, or blue. I think it's red, green, and blue. I might be off on that. And then what ends up happening is that kind of makes the picture on your old school TV. Now, new TVs operate differently than that. But literally that's why it had to be so deep, is that there was like an electron gun inside of it. Now, J.J. Thomson was actually working with the cathode ray tube, only obviously he wasn't watching TV, right? But he didn't know what he was using. He didn't even know that they were called electrons yet. He called them cathode rays because they were a ray of beams of stuff that he had seen before. But he had no idea what they were. Here's what he did know, and you might want to write this down here. He knew that they were very, very small. He could actually determine their mass. The smallest known element before Thomson did his work, the smallest element in the periodic table is hydrogen. Well, when he was working with these cathode rays, he discovered that cathode rays were 1,000th as small as hydrogens. I'm going to write that down here. These cathode rays, they were 1,000th as big as hydrogen. And this was actually really important. Because previous to this, John Dalton had a theory. John Dalton's theory was that atoms were as small as you get. You cannot cut them in half. Does that make sense? Atoms are as small as you get. You cannot cut them in half. And the smallest atom we know about, the smallest one on the periodic table is hydrogen. And hydrogen is this big. And so previous to that point, they thought that this was as small as it gets. And then all of a sudden, Thomson starts messing around with these things that he called cathode rays. And when he weighed them, he discovered that they weighed this much. And I'm not even doing it justice. It was 1,000 as big. This was revolutionary because it clearly meant that the smallest thing wasn't an atom anymore. And maybe you guys have heard this term before. We now know that there are things called subatomic particles. Anyone ever heard the word subatomic particles? There's actually 3 we know of. Protons, neutrons, and electrons. And so this was really instrumental because that whole indivisible concept was wrong. Now, scientists to this day are still working on, well, what are they made out of? Elements, we now know are made out of subatomic particles, things like protons, neutrons, and electrons. If you guys keep taking chemistry and physics with me, I'll eventually teach you about how we think that electrons are made up of things called quarks. And some scientists, if you guys watch Big Bang Theory, this is what Sheldon does on Big Bang Theory, they believe that quarks are made up of things called strings. And my personal belief is that scientists are never going to stop trying to figure out, well, what's this made of? Well, what's this made of? Well, what's this made of? They're always going to be trying to figure out, well, what's smaller than this? It's really hard to test that, though, because we're talking like super infinitely small. But back to J.J. Thomson. J.J. Thomson did this experiment in a tube here, and it basically is a prehistoric TV. Okay? What ends up happening is he shot electrons, that's what the pink is right here, and as the electrons went through the circuitry, they either kind of went straight or they deflected up and down. Now, because they took up space, they possibly could be matter. But because they deflected, it also meant they had a mass. And he was able to calculate their mass. And this is the thing I need you guys to know. They were not just smaller than the smallest previous item. They were way smaller than the smallest previous item. Which meant that, this is really the word you need to have here. He realized that there were subatomic particles. So he had a theory. Here's his theory. He suggested that maybe an atom is made up on the inside of the atom of little dots. And he knew they were negatively charged. That's why he called them cathode rays. We now call them electrons. You guys have heard the word electron, right? We now call them electrons. And he had this idea. He thought that maybe an atom was like a solid sphere, but that inside the atom were these little dots of negative charge. And that each of these dots was 1/1000th as big. So like this guy right here would be 1/1000th as big as the whole thing here. That was his thought. And as a way to illustrate it, he referenced it kind of like a popular dessert at the time. Now, we don't probably use plum pudding anymore, but that's what they had at the time. Basically what it was is it was, think of like maybe a muffin maybe. Inside the muffin you might have, say, chocolate chips. The chocolate chips would be the electrons, and the doughy part of the muffin would be the rest of it. And that was his theory, is that this is a sphere, and inside are these like chocolate chips. Only in his term, they would be raisins, basically. Does that make sense? And so he thought that inside, there must be these negative bits. Now, Thomson was actually right, because there are negative pieces called electrons. But he was actually wrong about where they were. But it wasn't until the turn of the 20th century that we actually discovered this. The next scientist I want to talk about, his name is Ernest Rutherford. Okay, a couple of side notes here. Ernest Rutherford actually worked in Canada for a while in his life. He worked at McGill University. And this discovery happened, I didn't write it down, I believe it was in 1907, I think. I'm trying to think back to my physics class. We were talking about this. It was in 1907. We're talking like 100 years ago. It's actually very recent in the grand scheme of things. And he did a very, very famous experiment trying to figure out again what matter is made of. Let me describe it to you with like some manipulatives. Okay. Got some pens here. Here's what Rutherford did. He took some particles that were very small. We now call them alpha particles, and I don't need you guys to know that. But he took some alpha particles, and he tried to shoot them at gold foil. And so I'm going to perform the same experiment with pens and a whiteboard. I'm going to throw a pen at a whiteboard. Okay, what happened? They bounced off, yeah. Which is totally what you would expect. He shot these particles at gold foil. I've got a picture here. He's got a particle, he shot these particles at gold foil, and you would think they would bounce off. And you know what? A couple did. A couple of them bounced backwards. But here's the most incredible thing. Most of the particles actually phased right through, which makes no sense, because when I threw my pens at the wall, they clearly hit and stopped. But what this would be like is if I threw the pen at the wall and it phased through into the hallway on the other side. That's literally what happened as an experiment. It's like a mutant off of X-Men. I throw something towards the wall, it does not hit the wall, and it phases through. Now, Rutherford could accept the fact that it phased through. He was like, okay, fine, it phases through. That's really weird. I don't get how it goes through. But here's the most unbelievable part. Then why did two of them bounce backwards? Let me say that again. First of all, it made no sense that as he shoots all these particles at the gold foil that most of them would go through. Because you'd think that they would just hit the wall and bounce back, right? But almost everything phased right through the gold. Except for a couple. And this was like, okay, how does everything phase through except for two? This makes no sense. He actually wrote down, I believe the quote was in his journal, he said it was like shooting an artillery shell, like a big gun, basically, at a piece of tissue paper and having it bounce back at you. That's what he said. It was like shooting an artillery shell at tissue paper and having it bounce back at you. It was like, it made no sense. Why is it not phasing through like the rest of them? So he came up with a new idea, and this is what you should really underline here. He came up with the idea of what if there is a nucleus to an atom? The idea behind a nucleus is that all of the matter is actually in the middle. And then surrounding the nucleus, all those little negative electron bits, that they're actually on the outside. And so if you were to draw a picture, it would look something more like this. You'd have a nucleus, and then a bunch of electrons around it. And then you'd have another nucleus, and a bunch of electrons kind of orbiting around it. And then a nucleus, which a bunch of electrons orbiting around it. Now imagine that I shoot something towards this. Let's say I shoot something right here. You guys see how it would phase through? And if I shoot something right here, it phases through. But once in a blue moon, if I shoot something towards it, it might actually randomly hit that small, localized mass and bounce out. And that was his idea. He suggested that what if it's not a ball that looks like this? What if it's not a solid ball with little bits in the middle? Right, see how I put all the bits in the middle? This is the previous idea. What if it was actually like a ball still, but all of the main stuff was in the middle, and all of those negative electrons, what if they orbit it? And he had an inspiration. His inspiration was our solar system. So brief aside, you guys know how in our solar system, there's the sun in the middle, and then the planets orbit around it. Well, this was his theory. He said, what if the nucleus, what if all of the matter, almost all of the matter is condensed right in the middle, like the sun, and what if there's electrons going around it? Now, they knew electrons existed because Thomson already proved that. But the real change is, rather than the electrons being inside the atom, he's really shrinking this down really small and putting the electrons outside of it. It's a brilliant idea. He said you have a nucleus. We actually use the word orbitals to describe the idea that these electrons right here would be orbiting around the nucleus. But Rutherford had a problem. Now, if I have my dates right, Rutherford posted his findings in like 1907. In 1909, he already knew he was wrong. And one of the reasons he knew he was wrong was based on the work of a guy named James Maxwell, who I don't need you to know, but Maxwell discovered some principles of electric charges, and one of them is that when you have a moving electric charge, it gives off radiation. Okay? Now, here's how this applies to his theory, and he knew he was already wrong. These electrons, if they really are orbiting, they're moving. And electrons are charged, which would then mean by his interpretation that every single piece of matter would be giving off radiation, which means we'd all be dead, right? Because if literally all electrons, if electrons that are moving give off radiation, according to another theory, and if his theory is right, these electrons are moving, then all matter, you, me, that table outside my car, everything would be giving off radiation. It means we'd all die from radiation poisoning. So, although he had a great idea, he knew he was wrong almost immediately. But he kind of stuck with the idea of the nucleus for a while. So here's kind of one more picture of kind of the idea here. It made no sense that these particles would phase right through. But hypothetically, let's assume that they can. Why would they bounce? Well, it's that compacted nucleus idea. Well, like I said, 2 years or so after Rutherford published his findings, he already knew he was wrong. but he was working with another scientist in about 1909 named Niels Bohr. And Bohr had an idea that also revolutionized the field, and it does to this day because scientists are still trying to figure this out. Bohr realized that these electrons, they cannot orbit, they can't go around because it would give off radiation if they did, and then we'd all be dead. So they clearly aren't going around in circles. But he had a new idea. Rather than calling them orbitals, he decided to call them energy levels. And I'm going to draw a bit of a picture again. Okay, I'm going to draw a nucleus right here. And I'm going to draw, again, I'm going to draw rings, just like you might imagine there being of like a planet. Now, here's the key difference though. Rutherford thought that an electron, I'm going to go stand at the board by the way. Rutherford thought that electrons literally did this. They just went around in circles for forever. Like that. That was Rutherford's idea. Bohr had a different idea. Bohr said, what if the electrons don't actually orbit? What if they exist in these energy levels? And what if they can move between energy levels? And this theory is so crazy, because here's what he suggested. He suggested that if an electron was right here, I like to use E's for electrons, he suggested when it moves, it could move from this ring out to this ring right here. But it doesn't just move like this. He suggested literally that it teleports. I'll say this again. Bohr suggested that what's actually going to happen is if an electron moves, it doesn't go around in circles. That literally it goes from here to here instantly, and that you'll never find it halfway in between. He actually had some evidence for this. He used some glowing tubes. And I can't really explain this well to grade 9 because you need to learn some more stuff first. But he had some glowing tubes where he got like one beam of red light here, one beam of blue light, one beam of purple light. I'm sorry if you guys can't see that all that well. And what he suggested this evidence meant is that the electron could live here, the electron could live here or here, but you would never find the electron in between. Never, ever. In the same picture, he suggested you'd never find the electron right there. And believe it or not, we actually believe this still to be true to this day. And scientists are actually working on teleportation based on this idea, where literally the electron goes from this energy level instantly over to here. You would never find it halfway in between, which is like crazy sci-fi type stuff. I watched a documentary with my physics kids about how there's some scientists working in the Canary Islands, I think it was, trying to teleport particles, literally just one particle at a time right now, from like one island to the other, using this kind of concept. It's crazy cool stuff, and it's not just science fiction. So here's what I need you to know about Bohr. Bohr's main idea, though, was to abandon the orbital concept. Rather than things orbiting, he suggested these electrons either exist here, or here, or here. And they literally did just jump and hop. And as we've learned more about physics, this has actually become proven true. Here's one of the reasons why. I'll give you an example here. How do I know that, Andrew? How do I know that Andrew is actually sitting here? Well, I can see him. Okay, let's talk through the why I can see him. Why can I see him sitting here? The light bounces off of him. Yeah, literally what's happening is light from the light bulb is bouncing off of him, and it bounces off of him to my eyes, and therefore I perceive him. Let me give you a different example. You know how it's like someone who's blind, how they might have like the stick they use in front of them? Well, it's kind of the same sort of idea. If they poke something and they feel it in front of them, then clearly there's something in front of them. In a way, light is bouncing off of him into me, and that's how I know that there's somebody there, right? Because it's bouncing off of him. Now, pause for a second here, though. Let's say we're talking about electrons. Electrons were 1/1000th as big as the smallest thing you know. They are so small that here's what happens. When light hits an electron, the electron moves. Imagine if he was an electron right here. As the light hits him and bounces towards me, I perceive him. But let's say the light wasn't like just light. Let's say that it was actually like a big shove. What would end up happening is as the light comes and hits him, he'd get flung way over there because he's so small. Now, I would still perceive the electron to be right there because the light came, bounced, hit off of it, and landed here. But is he still there? Well, no, he's so small that even light hitting it can cause him to move. And this causes a huge problem in physics because we cannot actually tell where stuff like matter, like electrons, we cannot tell where electrons are. We can tell where they were, though. Does this make sense? Electrons are so small that as soon as I look for them, they're already gone. Because the mere presence of looking for them, the light that hits them, actually causes them to move. And it makes it so hard to find where these electrons are. And that's what leads to our last model, which is the current one we're talking about. It's called a quantum model. The key word I need you guys to know about quantum models is it's all about probability. Because these electrons are so small, as soon as I look for them, they're gone. I hope everybody gets what I'm referring to here. Okay? The reason why I know that he's there is that light bounces off of him and comes to my eyes. But as the light bounces off him and comes to my eyes, has he moved? No. But if he was an electron, you'd be so small that if light were to hit you, you would literally go flying the other way. Now, I would get that reflection to my eyes, and I would think he was there. But is he still there? No, he moved. And so based on that, scientists now employ what they call a probability model, where they say, well, this is where we think he is or was and might have been. And it's very, very confusing. So I don't need you guys to know much more than just the idea of probabilities. Let me finish with this picture, and then I'll call it a day. This is what scientists nowadays use to draw pictures of atoms. And maybe you've seen something like this before. We call these probability clouds. Probability clouds. We actually still use the word orbital. Even though Rutherford knew that things don't orbit anymore, we still use the word orbital. But sometimes you see the word probability clouds. Here's how this works. Okay? We still believe that in the nucleus are all the protons and neutrons. All of the matter, most of it's in the nucleus. But, see this like little leaf kind of thing right here? What scientists believe here is that somewhere in that leaf is an electron. Somewhere. We don't know where. Because as soon as we look for it, it's gone. And so they use kind of like shapes to describe where they think they are. Hello. Yep. Okay. Okay. Sutak, you're supposed to go check out in the office. Okay. I'm almost done, I promise, guys. So the idea is that electrons are found inside these clouds, but we don't know where in the clouds they are. But here's the more crazy thing. We believe the electrons can jump from this cloud to this cloud. However, you will never find an electron right here. It literally goes from this cloud directly to that cloud by essentially teleportation is the idea. And it goes instantly from there to there. And that's what Bohr kind of discovered. Bohr's evidence was these like colored rings. And if you want me to try to explain that better, I'll do my best. It does involve some more knowledge of like stuff we haven't learned yet. But that's kind of the main concept, is that these three theories should go together. Okay. Rutherford believed that they orbited, but he instantly knew he was wrong. He knew he was wrong. Bohr suggested, what if they don't orbit? What if they exist in energy levels, where they literally bounce from one level to the next and they teleport? He was closer. Nowadays, we believe that these things live in clouds, probabilities as to where they could be. And again, we believe that they can bounce from one to the next. Basically, they're teleporters. Most science fiction is actually based on science. Okay, I think that's my last slide, right? Okay, so I've been talking for a while. Let me give you a quick summary, and then we guys can take off. Today, my goal was to talk with you guys about the history of how scientists slowly but surely have learned what matter is made of. Okay. I need you guys to know these scientists. I need to know some of their contributions, a lot of the terminology into things like orbitals, electrons, their models of the atom, things like the planet model of the atom, the plum pudding model of the atom. Okay? So if I can give you guys some advice, I know that it's just about time to take off here. Okay? But if you have some time during Flex today, a great idea would be to spend 10 minutes or so working on a few questions. If you do a few questions on your assignment every day, it's a lot easier. Okay, last thought that you guys can take off. Tomorrow we're going to do one more lesson, and then Wednesday I'm going to give you guys some work time. Because of the fact that we don't have school on Thursday, there's two things that are going to be due on Wednesday. Okay? Just so you guys are aware of time. Can you guys give me one more minute of attention and I'm done, I promise. I promise. Okay. Your lab safety project. Finish it by Wednesday. Your lab, finish it by Wednesday. Next week, Monday, though, we're going to do our first quiz. I don't have quizzes here. We're going to do our first quiz next week, Monday. The advice I would give, try to finish your assignment before the quiz. That's a good way to study for it. Because the answer key is on the sidewall. If you guys can mark that before you do your quiz, that'll help you do better. Okay? Okay, I'm done talking. We'll see you guys later. Thank you.